By the time this ship arrives, everyone who agreed to build it will be dead. So will their children. So will their children's children. Send a crewed ship to another star without breaking the speed of light, and the trip will never fit inside one lifetime. It will take centuries. The ship will not really carry travelers. It will carry a civilization, sealed inside a hull, spinning slowly for gravity, expected to grow its own food, repair its own machines, govern itself, and raise children who never chose the voyage they were born into. Tonight is not about whether we could build such a ship. It is about whether, once sealed inside, it could survive itself for that long. Get comfortable. This story spans centuries, so we are not going to rush it. Before we design a single deck of this ship, you deserve a fair question answered. Why not just go faster? It is the first thing almost anyone asks. If the real obstacle is time, why not build an engine strong enough to make the trip in a single lifetime, so nobody has to be born and die between the stars? A fair question deserves a real answer, not a wave of the hand. So let us take it seriously, one option at a time, and see where each one actually leads. The first option is the obvious one: go faster than light itself. Here, the honest answer has to start. Because this is not a matter of better engineering or a few more decades of research. As far as we understand physics today, the speed of light is not a difficult limit to push past. It behaves more like a wall built into the fabric of space and time. Albert Einstein's work on relativity, now more than a century old and tested again and again without exception, shows that as any object with mass approaches the speed of light, the energy needed to push it faster does not simply climb, it climbs toward infinity. No stronger engine gets around this. The problem is not that we have failed to build one yet. The problem is that the request itself does not make sense inside the physics we have. So light speed is off the table completely. There is a second idea, though, one that sounds almost like a loophole. It is worth sitting with, because it happens to be genuinely real. Time itself does not move at the same rate for everyone. This is not science fiction. It has been measured directly, with real clocks flown on real aircraft and satellites. The faster you travel, the slower time passes for you relative to someone who stayed behind. Push a ship close enough to the speed of light, and a crew could, in principle, cross an enormous distance while experiencing only a fraction of that time themselves. A journey that takes centuries back on Earth might feel like only a few years to the people on board. For a moment, this seems to solve everything. It does not solve the one problem that actually matters, which is getting the ship up to that speed in the first place. Every extra bit of speed costs energy, and near the speed of light, that cost stops behaving the way it does at ordinary speeds. It does not rise steadily. It rises so sharply that accelerating even a modest, crewed vessel to a meaningful fraction of light speed would require more energy than humanity produces in a year. That is before accounting for the fuel needed to slow back down at the other end, carry that fuel on board. And its own mass becomes part of the problem you are trying to solve. Since now you need extra energy just to accelerate the fuel meant to accelerate you. Engineers call this the tyranny of the rocket equation. At relativistic speeds, it stops being a saying and starts behaving like a locked door. Some proposals try to sidestep this entirely, building engines that carry no fuel at all, pushed instead by light or by particles collected from space itself. A few of these could plausibly send a probe the size of a postage stamp to a nearby star within a couple of decades. That is real, active research, and we will return to it later. Scale that same idea up to something large enough to keep a crew of living, breathing, eating people alive for the trip. Though, and the numbers stop cooperating. Fast and tiny stays within reach. Fast and inhabited does not. So we cannot go faster than light. And we cannot afford to go fast enough for time dilation to meaningfully help a crewed ship. A third option comes up almost immediately in any honest conversation about this. What if nobody has to be awake for the trip at all? Put the crew to sleep. Slow their bodies down until years pass in what feels, to them, like an afternoon. It sounds like a solution borrowed from a film. But it is not fiction filling in for missing science. It is an active field of research, funded right now by NASA, a company called SpaceWorks Enterprises, working with NASA, has spent years developing a concept for putting astronauts into a state called torpor, essentially a medically induced hibernation, for future missions to Mars. The idea borrows from a real and existing medical practice called therapeutic hypothermia, already used to protect patients after cardiac arrest, adapted here to slow an astronaut's metabolism for the journey. The engineer who has led much of this work, John Bradford, has described a future where a crew barely experiences the transit at all, waking up rested near their destination instead of spending months awake in a cramped ship. It is promising work, and it may well change how we send people to Mars. Look closely at the timescale it is actually built for, though. The research on human torpor for spaceflight is aimed at journeys measured in months, a trip to Mars and back, not centuries between the stars. Right now, we do not have the basic infrastructure to study long-duration hibernation in space at all. NASA's own recent research program on this, aimed at animals rather than people, describes itself as a first step, a foundation for studies that have not been run yet. Getting from months of induced sleep to centuries of it is not a small next step. It may not be possible for a human body at all, and nobody currently working on this claims otherwise. So here is where honesty about each option leaves us. Instead of just hoping one of them works, we cannot outrun light. We cannot afford the energy to make relativity do the work for us. Not with a crewed ship, and we cannot yet put a body to sleep for anywhere close to the length of time this trip would require. One option is left standing, not because it is elegant, and not because anyone is especially excited about it. It is left standing because the physics and the engineering we actually have ruled out everything else. If humanity ever sends a crewed ship to another star, the people who arrive will almost certainly not be the people who left. They will be the great-grandchildren of the people who left, possibly many generations further than that. Sit with that for a moment. Building something you will never see finished, for the benefit of people you will never meet, who did not ask to be born into the middle of your project, is a strange kind of decision to make. Looked at plainly, it is also one of the most patient things a species could ever choose to do. The real design problem, in other words, was never the engine. The real design problem is how you keep a small, sealed civilization alive, sane, and functioning for longer than most empires in human history have lasted. That is the ship we are going to build tonight, piece by piece. The first piece, the one everything else depends on, is a single number. Exactly how far away is far enough to matter, and exactly how long a trip like this would take. Start with the star, because the answer is smaller than most people expect, and somehow bigger than it sounds too. The nearest star system to our own is called Alpha Centauri, a group of 3 stars bound together by gravity, sitting so far south in the sky that most people in the United States and across Europe have never once picked it out with their own eyes. 2 of those 3 stars, Alpha Centauri A and Alpha Centauri B, closely resemble our own Sun. The third and faintest, a small red star called Proxima Centauri, sits just slightly closer to us than the other 2, close enough to hold the title of the single nearest star to Earth. Our own Sun aside, the whole system is close, only the way a lighthouse across an ocean is close. It sits about 4.2 light-years from where you are right now. Light-years describe distance, not time. But the easiest way to feel the size of one is to remember what light itself does. Light is the fastest thing that exists, and it still takes over 4 years, traveling every second of every day, to cross that gap. Nothing in the physical universe beats light to its destination, so 4.2 years is the fastest any signal, any messenger, any hope of contact could travel there. That is our flaw. Everything else is slower. How much slower? Let us ground this in something real. Something already out there, in the dark, right now. In the 1970s, NASA launched a spacecraft called Voyager 1. It is, at this moment, the most distant human-made object in existence, still transmitting a faint signal back to Earth after decades of travel, moving through interstellar space at roughly 17 kilometers every second. That is genuinely fast by the standards of anything we have ever built. Voyager 1 is not headed toward Alpha Centauri. It was never aimed there. If we could somehow point humanity's fastest, the farthest traveler directly at our nearest neighboring star and let it fly, though it would still take something like 70,000 years to arrive. 70,000 years. Set that beside 4.2. The gap between what light can do and what our best engineering has done is not small. It is nearly the whole width of the problem. Can we do meaningfully better than Voyager? Yes, at least for something very small. In 2016, an initiative called Breakthrough Starshot, backed by the investor Yuri Milner, proposed something that sounds almost too simple to work. Skip the fuel entirely. Build a probe smaller than your hand. Attach it to a thin reflective sail and push it from the ground using an enormous array of lasers rather than an engine it has to carry. On paper, a system like this could accelerate a sail to roughly 20% of the speed of light, fast enough to reach the Alpha Centauri system in only about 20 years. That is a real proposal, actively being researched, and it would represent the fastest journey to another star ever attempted. 20 years instead of 70,000. That is the kind of leap that makes any of this feel newly possible. But notice the size of what is actually traveling. A sail like this is built to carry a chip, not a crew. Nothing on the drawing board today can push something large enough to carry food, water, breathable air, and living people up to a meaningful fraction of light speed. The energy required does not scale up gently. It scales up brutally the moment you add real mass to the front of that sail. Fast and tiny remains within reach. Fast and inhabited does not. There is a second problem tucked inside the first one, and it rarely gets mentioned. Getting up to speed is only half of any trip like this. A ship that reaches Alpha Centauri while moving at a real fraction of light speed does not arrive there in any useful sense. It simply passes through, faster than any instrument on board could study anything, faster than any crew could ever hope to slow down, look around, and land. To truly arrive, the ship has to shed nearly all of that speed again on the way in. Whatever energy it spent speeding up, it needs to spend roughly that much a second time, just to stop. Every fast, elegant proposal for reaching another star quietly doubles its own hardest problem the moment you ask it to actually stop when it gets there. That doubling is easy to forget when a headline number like 20% of light speed is doing all the talking. It quietly reshapes every proposal we look at from here forward, including the one built specifically to carry people. The actual number that matters for the ship we are building tonight comes from turning the whole question around. We already accepted, back in the last chapter, that this trip will take generations either way. So, the real question changes shape. It is no longer how do we go as fast as possible. It becomes, what is the slowest, gentlest, most survivable speed that gets a ship there within a length of time a civilization on board could actually plan around. Recent serious engineering studies of crewed interstellar ships tend to settle on a mission length of around 250 years for a trip to the Alpha Centauri system. Do the arithmetic. 4.2 light years. Covered over 250 years. The cruising speed such a ship would need works out to only a little under 2% of the speed of light. Not 20%. Not close to it. Something far gentler. Well within reach of propulsion ideas that already exist on paper. Some of which we will look at directly. Do not mistake gentler for slow. 2% of light speed still works out to something like 6,000 kilometers every single second. That is fast enough to cross the entire width of the continental United States before you could finish reading this sentence out loud. It only sounds modest, sitting next to something as extreme as 20% of light speed. Next to anything a human being has actually built and flown. It remains almost unimaginably fast. That is the quiet twist sitting at the center of this entire question. The hard part was never really the speed. A generation ship does not need a miracle engine. It needs something closer to a very patient one. What it needs instead is everything else. 250 years of feeding people. 250 years of breathable air. 250 years of governments, marriages, arguments, and inheritance, playing out entirely inside a sealed hull, with no way to call home and get an answer back in less than about 8 years round trip, at the speed of light, let alone in any useful amount of time at all. Sit with that 8 years for a moment, because it changes what a message even means. Send a question the day the ship launches, and the answer will not arrive until whoever asked it has aged nearly a decade. If they are even still checking for a reply by then, every later message only gets slower relative to a life actually being lived. A birth announced from the ship would reach Earth as old news about a stranger nobody there will ever meet. A piece of advice sent back from Earth would land in a version of the ship's culture that may have already moved past the question being asked. For all practical purposes, once the ship is a few years out, it is not really in conversation with home anymore. It is simply informing Earth, after the fact, of decisions Earth had no chance to weigh in on. Break 250 years down into something more human. You are talking about 8 or 9 full generations, living, working, and dying between departure and arrival. Grandparents who will never meet the great-grandchildren who finally step outside. A newborn, on the day the ship leaves, could be dead of old age before the ship is even halfway there. So now we know the shape of the problem. Roughly 4.2 light years to cross. Roughly 2 centuries and a half to do it in. A cruising speed so modest it almost feels anticlimactic after everything we just ruled out. Somebody had to be the first person to sit with these same numbers and reach that conclusion. The answer to the engine question was never a better engine. It was a ship built to be lived in. Exactly when did anyone first take that idea seriously? The answer has a name attached to it that might surprise you. Because it is not a science fiction writer. It is the man most Americans learned about in school as the father of modern rocketry. In January of 1918, more than 6 years before he began his first experiments with liquid propellant rockets, a young professor named Robert Goddard sat down and wrote an essay he titled The Last Migration. He did not publish it. He did not tell most of his colleagues about it either. Instead, he sealed it inside an envelope, handed it to a friend for safekeeping, and wrote on the outside a far more boring label, describing it only as notes on high-altitude research. Inside, he left a private note suggesting that whoever eventually opened it should be, in his own words, an optimist. What Goddard had written inside was not a plan for reaching the moon or Mars. It was a plan for the day the sun itself grew too cold to keep Earth alive, and what humanity might do about it. He imagined expeditions launched outward toward regions where stars cluster more thickly together, carrying with them a condensed record of everything the species had ever learned. Its literature, its art, its tools, so that if they ever arrived somewhere new, a civilization could begin again. For the vehicle itself, Goddard did not picture something built from scratch. He imagined something found and hollowed out instead. An asteroid, or a small moon, converted into a home, because he understood, better than almost anyone alive at the time, just how far away everything truly was. Goddard did not imagine a crew staying awake for the trip. He imagined the human body reduced nearly to nothing, dried down to what he called a granular state, capable of surviving the cold of deep space, then carefully revived at long intervals along the way. A pilot would be woken only once every 10,000 years for a trip to the nearest stars, and only once every million years for anywhere farther, kept on schedule by a clock powered by radioactive decay. He even considered, seriously, that whoever finally arrived after such a journey might not fully resemble the people who left. None of this saw daylight while Goddard was alive. By every account, he was a private and almost fearful man when it came to his most extreme ideas, terrified of being written off as a crank. The essay stayed locked away for decades, surfacing only long after his death. Once the idea itself had already occurred to other people, quietly and separately. One of those people was a Russian schoolteacher and self-taught scientist named Konstantin Tsiolkovsky, often credited as the founder of modern astronautic theory. Around the same period as Goddard, working independently, without any knowledge of Goddard's sealed envelope, Tsiolkovsky described his own version of the same idea, a traveling space colony, carrying multiple generations of passengers toward a new home. One he described simply as an ark. Two men, one in the United States and one in the Soviet Union, separated by an ocean, a language, and a political divide that would only grow deeper as the century went on, stared at the same underlying physics and arrived, independently, at nearly the same conclusion. But it was a third man who actually put the idea in front of the public, making it something other thinkers could argue with, build on, and try to design. In 1929, an English scientist named J.D. Bernal published an essay called The World, the Flesh, and the Devil. It was not really a piece about spaceships. It was a wider argument about the obstacles standing between humanity and its own future. Obstacles Bernal sorted into three categories: the physical limits of the world itself, the biological limits of the human body, and the irrational, self-defeating parts of the human mind. Almost as a side note inside that larger argument, imagining what might happen once the first of those obstacles was overcome, he sketched out a hollow sphere, built in space, spinning slowly to create gravity along its inner surface, home to a self-sufficient population that could, in principle, keep traveling indefinitely. It was philosophy more than engineering, closer to a thought experiment than a blueprint. It was public, though, and it stuck, decades later, when serious engineers finally sat down to design real rotating space habitats. Bernal's hollow sphere became the starting shape almost everyone returned to. For more than 30 years after that, the idea mostly lived exactly where Bernal had left it, in essays and speculation, discussed by physicists at dinner rather than drawn up on paper. That changed in 1964, when an engineer and physicist named Robert Enzmann proposed something with actual dimensions attached to it. Enzmann's design called for a ship roughly 600 meters long, built to carry an initial crew of around 200 people, with room designed in from the start for that number to grow. Instead of Goddard's hollowed asteroid or Bernal's abstract sphere, Enzmann proposed something closer to a true vessel, powered by nuclear fusion, burning a fuel called deuterium to reach speeds that, while nowhere near light speed, were fast enough to make the trip within a human-relevant span of time. It remains one of the most detailed generation ship designs ever put on paper. Notice the shape of that whole story before we move on from it. A rocket scientist, too afraid to say it out loud. A schoolteacher who reached the same conclusion alone, on the other side of a closed border. A scientist who finally said it in public, dressed as philosophy, so it would be taken seriously. Then, at last, an engineer willing to put real numbers on a page. It took 4 different people, working decades apart, mostly without knowing about one another, to walk the same idea from a secret to a sketch to something resembling a design. By the middle of the 1960s, the idea had traveled a long way from one rocket scientist's sealed envelope. It had a name, several competing shapes, and at least one engineer's serious attempt at blueprints. What it still needed was an engine anyone could actually imagine building. That very same decade, at a defense contractor in California, engineers had already begun testing a stranger, far more explosive answer to that exact problem. The answer, quite literally, was to build a spaceship powered by nuclear bombs. It sounds less like engineering and more like a dare. But the physics behind it is not complicated. A rocket works by throwing mass out behind itself and getting pushed forward in return. Chemical rockets do this by burning fuel. Project Orion asked a stranger question. What if, instead of a continuous burn, you threw small nuclear bombs out the back of the ship, detonated them one after another, and let a massive metal plate at the rear absorb each blast like a shield catching a series of hammer blows, converting each explosion into a forward push? The core idea came from the physicist Stanislaw Ulam, who first worked out the basic possibility in the late 1940s. Not long after helping design the weapons, this idea had borrowed its physics from in the first place. For about a decade, the concept remained mostly theoretical. Then, in 1958, it became a funded program, developed at a defense contractor called General Atomics in California, under a research arm of the American military that would later become known as DARPA. Two men ended up leading the effort. Ted Taylor, a weapons designer who understood better than almost anyone alive how to shape a small nuclear detonation, and Freeman Dyson, a theoretical physicist who left his post at Princeton for a year to help turn Taylor's intuition into real calculations. Together, with a growing team around them, they worked out a design: a blunt, heavy ship, a massive pusher plate at the rear, connected to the crew compartment through a system of shock absorbers, meant to smooth out what would otherwise be a series of violent jolts, one every second or so during the most intense phase of a launch. Dyson later looked back on this stretch of his career, some 15 months of it, as the happiest and most exciting of his entire scientific life. A striking thing for a physicist who also helped explain the fundamental behavior of light and matter to say about a project that never actually flew. Part of what he seemed to love was the sheer audacity of it. A small team in San Diego seriously believing they might personally travel to Saturn within a decade, working at a pace and a scale that Cold War-era defense money, for a brief window, made possible. It was, on paper, staggeringly capable. Thrust and payload capacity far beyond anything chemical rockets could offer. Enough, the team genuinely believed, to carry dozens of astronauts and hundreds of tons of cargo anywhere in the solar system. Their internal motto, only half joking, was reportedly something close to Mars by 1965, Saturn by 1970. Remember, this was before a single human being had even reached orbit. The idea was taken seriously enough. In fact, that Werner von Braun himself, the engineer who would soon lead the conventional chemical rockets that actually carried astronauts to the moon, wrote his own paper advocating for it. This was not a fringe idea confined to a handful of enthusiasts. Some of the most respected rocket engineers alive at the time thought bombs might genuinely be the answer. Some inside the project dreamed even further than Mars and Saturn. Internal designs considered scaling the whole ship up to something on the order of 8 million tons. Large enough to function less like a spacecraft and more like a small floating city. In interviews given years later, some of the engineers who worked on it admitted they had genuinely pictured this largest version as a potential interstellar arc in its own right, long before Freeman Dyson ever put real numbers to that same idea on paper. Getting any version of this to work took more than welding together a metal plate. Each detonation would hit that plate like a hammer blow. Translating that kind of violence into something a human body could survive meant inventing an entire shock absorption system, several stages deep, mechanical springs paired with gas-filled pistons. Designed to stretch one sharp jolt per second into something closer to a smooth, continuous push a crew could sit through without being shaken apart. None of this stayed purely theoretical. In November of 1959, the team built and flew a small-scale model using ordinary chemical explosives instead of nuclear ones, just to prove the pusher plate and shock absorber concept worked. The model, nicknamed Hot Rod, flew under its own power for about 23 seconds, reaching a height of roughly 56 meters before parachuting safely back down. It is still preserved today at the Smithsonian National Air and Space Museum, a strange, almost toy-like proof that the basic mechanical idea was sound. Scaling this up to something that could reach another star meant leaving fission bombs behind and turning to something far more powerful. In 1968, years after the original program had already been shut down, Freeman Dyson published a paper called Interstellar Transport, working out what a much larger version of this same idea might look like using fusion explosions instead of fission ones. His numbers suggested a ship like this could be pushed to a meaningful fraction of light speed, fast enough, in his more optimistic design, to make the journey to Alpha Centauri. Notice what even Dyson himself concluded about the timeline. By his own estimate, even the faster of his two proposed designs would mean that only the grandchildren of the people who built it would actually live to see it arrive anywhere. Read that again. This was the single most explosive, most energetic propulsion concept ever seriously proposed by a working physicist, and it could not escape the conclusion we already reached 2 chapters ago. It was still, in every meaningful sense, a generation ship. It simply arrived at that same destination through a different door. There was even a strange kind of elegance tucked into some of the largest versions of this design. Dyson proposed that the pusher plate itself, the very piece of metal absorbing every detonation, could be made largely out of uranium, not for the explosions along the way. Instead, once the ship finally reached its destination, the crew could tear the battered plate apart and use it as raw, nuclear-engaged fuel for whatever came next. The single most radioactive, most abused part of the entire ship would become the starting power supply for a brand new colony. Other problems had nothing to do with politics. Dyson's own calculations suggested that a crew riding this close to repeated nuclear detonations would absorb something like 700 rads of radiation with every single blast, in an environment where roughly 1,000 rads is considered a lethal dose for a human being. Shielding a crew from that, blast after blast, for the entire length of a launch sequence, was never fully solved. It remained one of the program's quietest, least publicized problems, sitting underneath all the bold talk of Mars and Saturn. In the end, it was not the radiation that killed Project Orion. It was politics. In 1963, the United States signed the Partial Test Ban Treaty, prohibiting nuclear explosions in the atmosphere and in space. A ship that worked by detonating bombs behind itself was now simply illegal to test. Funding dried up. By 1965, after roughly 7 years and something like $11 million spent, the program was formally closed. Freeman Dyson later reflected that this was one of the only times in modern history a major piece of human technology had been shut down, not because it failed, but purely because of the political climate surrounding it. The bomb-powered ship never flew. The idea it left behind did not vanish, though, within a few years, a different group of engineers, working without any nuclear weapons at all, picked up the same basic question Ulam and Taylor and Dyson had been asking, and tried to answer it a second time, using an entirely different kind of explosion. Bombs were not the only answer to come out of that same era. Understanding what came next means understanding a choice almost every serious propulsion idea has had to make ever since. Do you build something that could plausibly carry people, or do you give up on people entirely and build something small enough to actually reach relativistic speed? Between 1973 and 1978, a group of about a dozen scientists and engineers working for the British Interplanetary Society, led by an engineer named Alan Bond, chose the second path on purpose. Their project was called Daedalus, and unlike Orion, it never pretended to carry a crew at all. The British Interplanetary Society was not some fringe hobbyist club dabbling in speculation, founded back in 1933. It remains one of the oldest space advocacy organizations in the world, and Daedalus is still, to this day, one of its most cited and most seriously regarded technical studies. Daedalus was designed as a two-stage, unmanned probe, powered by nuclear fusion rather than fission bombs. Instead of exploding whole nuclear devices behind the ship, Daedalus was meant to ignite tiny pellets of fuel, a mixture of deuterium and a rare isotope called helium-3. Using powerful electron beams, picture something closer to a miniature continuous combustion chamber than a single blast. Each pellet, smaller than a grain of rice, would be struck by focused beams of electrons, compressing and igniting it in a fraction of a second, over and over, something like 250 times every second during full thrust. The first stage alone was designed to burn for a little over 2 years, accelerating the probe to about 7% of the speed of light. That stage would then be discarded, and a second stage would ignite, pushing the probe further, up to around 12% of light speed, before shutting down and letting the probe coast the rest of the way in silence. Notice how quickly this all happened, one idea after the last. Orion collapsed under its own treaty by 1965. Daedalus began its own serious study less than a decade later. This was never a field moving slowly out of disinterest. It kept finding new reasons to try again, using whatever tools each new decade made available. At that speed, the design team calculated a journey of about 50 years to reach their original target star. Retarget the same design at Alpha Centauri instead, and the number drops to somewhere around 36 years. For an unmanned probe carrying only instruments, with no life support, no food, no need to ever slow down or stop. This was a genuinely serious, carefully engineered proposal, not science fiction dressed up as science. There is something worth noticing in the choice of fusion pellets over whole nuclear bombs. Daedalus never ran into the treaty problem that ended Orion, since none of its detonations counted, legally, as the kind of weapons test regulators had in mind when that treaty was written, and because no crew sat anywhere near the engine. The radiation problem that haunted Dyson's own calculations simply stopped applying to anyone. Daedalus did not out-engineer Orion so much as it quietly outmaneuvered the two specific problems that had actually killed it. The team behind Daedalus was honest about its own remaining problems, and one of the biggest had nothing to do with the physics at all. Helium-3, the fuel their entire design depended on, is extremely scarce here on Earth. Getting enough of it would likely have meant mining it somewhere else entirely, most plausibly from the surface of the Moon. A challenge the original 1970s study could only gesture toward, since nobody had ever attempted anything like it. Decades later, most of the obstacles Daedalus identified remain exactly that, obstacles, still unresolved. The study itself was never meant to end in a launch. Its authors said as much from the beginning, describing the exercise as a way of testing whether interstellar travel belonged in the realm of serious engineering at all, rather than science fiction. Using nothing but physics and materials a 1970s engineer could point to and defend, that modest, almost academic goal is part of why Daedalus still gets cited today, decades after the study wrapped, by teams working on entirely different propulsion concepts. It was never trying to be the final answer. It was trying to prove the question itself was worth asking seriously. And on that count, it succeeded completely. Notice, again, what this design chose not to be. Even at 12% of the speed of light, dramatically faster than anything a generation ship would ever need to reach, Daedalus carried no crew whatsoever. There was no version of the mission where a human being climbed aboard. The same is true of the laser-propelled sail concept from 2 chapters back, the one capable of reaching Alpha Centauri in only 20 years at a full fifth of light speed. Both are real, serious, still actively studied ideas. Both solve the speed problem by removing the one thing that makes speed expensive in the first place: a living, breathing person who needs to eat, drink, breathe, and survive the trip. There is a related worry that shows up constantly in serious interstellar planning circles. One worth naming here, before we leave propulsion behind for good. Some researchers call it an obsolescence problem. Launch a mission today using today's best engine, and there is a real chance that a faster mission launched 50 years from now, using technology that does not exist yet, could overtake it partway through the journey and arrive first. Wait for the better engine instead. And the same argument applies all over again to whoever launches 50 years after that. Taken seriously, this logic can talk a civilization out of ever launching anything at all, since something better is, in principle, always one more generation away. Most researchers who study the question conclude the trap eventually breaks on its own. Since propulsion technology cannot improve forever at the same pace, and a civilization that only ever waits for something better never actually goes anywhere. It is a useful thing to keep in mind. Though, for exactly the chapters ahead, if the goal shifts from winning a race to simply getting there, waiting stops making sense, and building starts to. This is the fork every serious interstellar proposal eventually reaches. Go fast, and leave the crew behind, or bring the crew, and accept that you are no longer racing against time at all. Neither choice is the wrong one. A fast, unmanned probe can still teach us almost everything we could hope to learn about a distant star system, its planets, its chemistry, whether anything there might support life. If knowledge is the only goal, sending an instrument is by far the more sensible plan. Knowledge was never the only goal hiding inside this question. Though, was it? Underneath all of this has always been a quieter, more stubborn hope that human beings themselves, not just their instruments, might one day stand under a different sky. A generation ship is what happens when you decide that hope is worth pursuing anyway. Not as a failure to go faster, but as the only honest response to a problem that speed alone was never going to solve. The actual engineering challenge in front of us has nothing left to do with engines. From here forward, every remaining question is about the ship itself, and about the people inside it. What does it have to be built like, physically, to hold a functioning, breathing civilization together for 250 years? That starts with the most basic requirement of all, something as simple and as complicated as gravity. Gravity is not something you can simply decide to have. Every astronaut who has spent extended time in orbit comes home with the same measurable cost. Bone density drops, sometimes by a meaningful percentage after only a handful of months. Muscles weaken, even with hours of daily exercise built into the schedule specifically to fight it. Fluids shift inside the body, changing how the heart works and even how the eyes focus. None of this is speculation. It has been documented for decades aboard space stations, on missions lasting only months. And it gets worse, not better. The longer a body stays weightless, send a population to live somewhere for 250 years with no gravity at all, including children born and raised there, who never once feel what solid ground beneath them is supposed to mean. And you are not designing a ship anymore. You are designing a slow, guaranteed medical catastrophe. Gravity is not optional. Then, here is the strange part. There is only one practical way to produce something that feels like gravity anywhere except the surface of a planet. And it is not some exotic future technology. You already understand it instinctively from riding in a car around a sharp turn, or swinging a bucket of water in a circle without spilling it. Spin something, and anything inside gets pushed outward, against the inside wall, hard enough to stand on. There is nothing mysterious about the physics, even if it feels that way. Real gravity pulls you down because a planet's mass is pulling on you. Spin gravity works in the opposite direction. Stand on the inner wall of a rotating cylinder, and the wall itself is what constantly pushes against you, curving your path inward instead of letting you travel in the straight line your body would otherwise take. Your body interprets that constant push exactly the way it interprets standing on solid ground. The bigger the wheel, and the slower it turns, the gentler and more convincing that push becomes. We already met the first person to sketch this idea seriously. Back in the last century, remember J.D. Bernal's hollow sphere from 1929, spinning slowly to hold a population against its inner surface. That idea did not stay a lonely thought experiment forever. In 1969, a young physics professor at Princeton named Gerard O'Neill posed what started as nothing more than a classroom question to his undergraduates. Was a planet's surface really the best place for an expanding civilization to live? If not, how large a structure could realistically be built in open space, using engineering that already existed? The answer his students worked out surprised even him. Structures tens of miles across were physically possible. O'Neill spent years developing the idea properly, publishing it formally in 1974. Then, laying out the full vision in a 1976 book called The High Frontier. This was not dismissed as fringe speculation. Between 1975 and 1977, NASA's own Ames Research Center ran a series of summer studies built around O'Neill's proposals, turning his classroom sketches into a detailed engineering report, published under the plain title Space Settlements, a NASA document with a NASA cover. Inside the High Frontier, O'Neill proposed 3 separate designs, growing in scale. The first, which he named Island 1, he described in his own writing as a modified version of Bernal's original sphere. The second was another, larger sphere. The third, and the most famous, became known as the O'Neill cylinder, a pair of enormous cylinders, each roughly 5 miles across and 20 miles long, spinning in opposite directions from one another, so their combined momentum would not fight against efforts to keep the whole structure aimed correctly toward the sun. Here is the detail worth sitting with. 47 years after Bernal sketched a hollow spinning ball almost as an afterthought inside a philosophy essay, a Princeton physicist working the actual engineering handed that same basic shape back, with real numbers, real materials, and a NASA study attached to it this time. Bigger comes with its own strange requirement, though one that is easy to miss. You cannot simply spin any structure fast and call it done. Spin something too quickly, and the human inner ear notices immediately, producing dizziness and nausea the moment anyone turns their head too fast. A problem engineers call the Coriolis effect. Research going back decades generally puts the comfortable limit somewhere around 2 full rotations per minute before this becomes a real problem for most people. Slow rotation, at that gentler pace, only produces a meaningful amount of gravity if the structure spinning is enormous. Small and fast feels like an amusement park ride. Large and slow feels, almost indistinguishably, like standing on solid ground. There is no way around this trade. If you want your crew to feel normal, the ship has to be genuinely, physically enormous. There is a second, quieter wrinkle tucked inside the same physics. One most casual explanations skip entirely. Gravity produced by rotation is not perfectly even from head to toe the way real planetary gravity is. Stand at the very center of a spinning cylinder, and you would feel almost weightless. Walk outward toward the rim, and the pull builds gradually the whole way. A tall person standing on the outer deck would, technically, feel a very slightly stronger pull on their feet than on their head, a gap called the gravity gradient. On a small structure, that gap is large enough to feel genuinely strange. On something the size of an O'Neill cylinder, miles across, it shrinks down to something the human body never notices at all. Scale, once again, turns out to be doing quiet, essential work behind the scenes. Not every serious modern proposal insists on building at that enormous a scale. Either, a later design study called Kalpana 1, put together by a team including the engineer Al Globus, worked out how far the size could shrink while keeping both the rotation rate and the gravity gradient inside comfortable limits. Their answer was a squat cylinder, only about 250 meters in radius and roughly 325 meters long, spinning at that same gentle 2 rotations per minute, sized to comfortably house a few thousand people rather than tens of thousands. Smaller means faster to build and easier to launch. It also means trading away some of the O'Neill cylinder's more generous scale. Every real design ends up trading one kind of discomfort against another. Cost against comfort. Buildability against how strange the physics feels to the people actually living inside it. Which is why serious modern designs for a ship like this do not look like the sleek, narrow spacecraft most of us picture. They look more like small, hollow worlds, wide cylinders or spheres, spinning patiently through the dark. Their interior walls doing the quiet work that a planet's own mass does for free back home. This is not an idea that faded into old textbooks either. In 2019, at a public event in Washington, the Amazon founder Jeff Bezos stood in front of an audience and argued that structures very close to O'Neill's original cylinders were still a better long-term bet than trying to terraform the surface of another planet. 90 years after Bernal, 50 years after O'Neill's classroom question, the shape has aged remarkably well. We know the shape gravity has to take. Then, we know it has been imagined for nearly a century. From a private essay, to a philosophy book, to a physics classroom, to a NASA report, nobody had yet tried to put every piece of this puzzle together into one complete design, using real, current science. In our own decade, that has already happened. The result has a name. Here is something worth pausing on before we go any further. Everything in this chapter is not a thought experiment from decades ago. It is happening right now, by people currently alive, currently working. In November of 2024, an organization called the Initiative for Interstellar Studies, a non-profit based in the United Kingdom, launched something called Project Hyperion. It was not a fundraising campaign, and it was not a piece of concept art. It was a formal design competition, open to teams anywhere in the world, with one enormous assignment: design an actual generation ship, not vaguely, in detail, down to how its people would eat, govern themselves, and pass their knowledge on to children not yet born. The name was not new. A researcher named Andreas Hein first opened a study under the same title back in 2011, tracing its roots to a student engineering group at the Technical University of Munich. For more than a decade, that early version of Project Hyperion stayed mostly academic, producing detailed papers on population size and habitat architecture, presented at workshops hosted by the European Space Agency, published in journals few outside the field ever read. The 2024 competition was the moment that patient academic groundwork finally opened its doors to the public and asked strangers around the world to actually try designing the thing. The rules were specific, and they were demanding. Any submitted design had to house somewhere between 500 and 1,500 people, comfortably, for centuries. It had to generate gravity through rotation. The same physics we just spent an entire chapter on. It had to include a fully closed-loop system for food, water, air, and waste, recycled essentially forever, with nothing coming in from outside once the journey began. It needed real, engineered radiation shielding, and, tellingly, every team had to include not just an architect and an engineer, but a social scientist as well, because the people running this competition understood something we have been building toward this entire episode. A generation ship that only solves its engineering problems and ignores its human ones is not actually a solution at all. Entries were scored against a fixed formula, not a panel's mood on the day. Technical feasibility counted for the largest share. followed by how resilient the design society seemed likely to be across generations. Then how sustainably its ecosystem could actually feed and breathe for that long, with polish and presentation counting for only a small slice of the total. A design could look stunning and still lose to something plainer that had actually solved the harder problems underneath. Teams from around the world entered. 50 made it through an initial concept round. 23 advanced to a detailed design phase. On the 23rd of July, 2025, judged by a panel that included A. Scott Howe of NASA's own Jet Propulsion Laboratory, alongside space architecture researchers from the University of Houston, the University of Southern California, and Arizona State University. The winner was announced, an Italian team, with a design they named Chrysalis. Chrysalis is worth describing in some detail, because the specificity is the entire point. The ship is envisioned as roughly 58 kilometers long, built from a series of nested, rotating shells, one inside another, each dedicated to a different function. Food production and ecosystems on the outer layers, communal gathering spaces and housing further in, workshops and storage, deeper still, all the way down to a central axial core. Some versions of the design even alternate the spin direction of neighboring shells, one clockwise, the next counterclockwise, specifically to cancel out unwanted rotational forces on the structure as a whole. At the very front sits something the designers called the Cosmodome, a viewing chamber near the axis, in much lower simulated gravity, where passengers could look directly out at the stars they were slowly crossing. Rather than locking in one fixed number of people forever, the design treats population as something that grows and shrinks naturally over the centuries, the way any real community does, staying inside the competition's required range instead of sitting frozen at a single count. Chrysalis was not the only serious answer submitted. A Polish team called WFP Extreme took second place, focused heavily on the cultural and spiritual side of a multi-century voyage, right down to designing clothing meant to work in both rotating and weightless sections of the ship. A third-place design, built around hiding the crew inside a hollowed-out asteroid for natural radiation shielding, rounded out the top three. Dozens of other teams from around the world received honorable mentions. This was not one lone group of enthusiasts. It was a genuine, global research effort. The judges did not simply crown a winner and move on either. Their published notes on Chrysalis read less like a trophy citation and more like a peer review. They praised the design's system-level coherence and its detailed plan for actually manufacturing the vessel in space. They also flagged real weaknesses: an imbalance between stunning artificial renderings and the underlying technical drawings, and a cultural governance plan the reviewers felt still needed more development. Even the winning entry, in other words, walked away with homework. For power and propulsion, the Chrysalis team chose a fusion system burning deuterium and helium-3, the very same fuel combination the Daedalus team had proposed more than 50 years earlier, aiming for a cruising speed of roughly 1% of the speed of light. Here is where the story gets honest in a way that matters. The competition brief asked for a mission length of around 250 years, the same figure we worked with 2 chapters ago. Once the Chrysalis team ran the numbers on their own real fusion engine at that speed, the true mission length came out closer to 400 years. Not a failure, not a design flaw, just the same unforgiving arithmetic we already introduced ourselves to earlier, catching up with a real, detailed, professionally judged design. Even the best paper starship humanity has produced so far still runs straight into the same wall the rest of us do. Perhaps the single strangest detail in the entire proposal has nothing to do with the ship at all. Before anyone boards Chrysalis, the design calls for several generations of the future crew's ancestors to live first inside an isolated, self-contained colony in Antarctica, 70 to 80 years of it. The goal is to observe how people actually behave and cope across generations of extreme isolation, before a single person is ever allowed near the real ship. Read that again. Before humanity is trusted to leave Earth for good, the designers of our most serious generation ship proposal want to test us. Generationally. On Earth first. Governance on board was handled just as seriously. Rather than a single fixed constitution meant to somehow survive unchanged for 4 centuries, the design proposes an ongoing partnership. Human population on one side, artificial intelligence systems on the other. Together, they share responsibility for the countless daily decisions that keep a closed civilization functioning. The judges and the designers understood something plainly. No political system written in 1 century reliably survives contact with the next one unchanged. The organization's own director has been fairly candid about why any of this matters. Even if a real chrysalis never leaves a drawing board in our lifetimes, the exercise forces a level of honesty that pure speculation never demands. A panel of NASA and university reviewers will not accept a handwave. You either work out how 10 generations govern themselves, or your design loses points. You either solve the radiation problem with real materials, or you do not. That discipline, the organizers have suggested, may end up teaching us as much about building resilient, long-term systems here on Earth as it does about ever actually reaching another star. That last idea is worth sitting with. Every one of the problems this competition forced teams to answer: feeding a closed population, governing across generations, preserving knowledge nobody currently alive will use for centuries, describes a challenge Earth itself is quietly facing on a longer timescale. Climate systems, aquifers, nuclear waste, retirement funds, institutions built to outlast the people who founded them. A generation ship is, among other things, human civilization's own long-term planning problem, compressed into a single sealed hull, small enough to actually study in detail. This is where things stand right now. In our own decade. Not science fiction. A funded, judged, publicly documented design, built by real architects, real engineers, and real social scientists. Wrestling, honestly, with a problem we have been circling this entire episode. We now have one possible propulsion pathway on paper: gravity. We already know how to solve. What remains is arguably harder than either. Once you seal several hundred people inside a spinning metal world for 4 centuries, how, exactly, do you keep them fed? Feeding a crew for 400 years sounds, at first, like the simplest problem on this entire ship. Grow food. People have been doing that for thousands of years. How hard could it be inside a sealed hull? Humanity has already tried to answer this question directly. Though, for real, with real human beings, sealed inside a real structure. The results were humbling enough that everyone designing a generation ship today still studies them closely. In September of 1991, 8 researchers walked into a 3-acre, fully sealed glass structure in the Arizona desert, called Biosphere 2, named for the simple reason that Earth itself was considered Biosphere 1. Their goal was straightforward on paper: live inside a completely closed ecological system for 2 full years, growing their own food, breathing air recycled entirely by their own plants, with nothing coming in or going out except sunlight and information. Inside the glass, the designers had packed an almost absurd variety of Earth itself: a scaled-down rainforest, a small ocean complete with a coral reef, a desert, a marsh, or savanna, alongside the working farm that was meant to feed everyone. It remains the most ambitious, closed ecosystem experiment humanity has ever attempted. The 4 men and 4 women inside, a group that included a medical doctor and several trained ecologists, worked hard. Farming alone consumed roughly a quarter of every waking hour, tending crops of bananas, papayas, sweet potatoes, beets, peanuts, rice, and wheat. By some measures, they succeeded spectacularly. Their half-acre farm became, per square foot, one of the most productive pieces of agricultural land on the planet, outproducing traditional farming communities in parts of Asia by several times over. There is a small, strange irony worth pausing on. The crew's own physician, a researcher named Roy Walford, had built much of his career studying whether eating fewer calories might help people live longer. Inside Biosphere 2, his own crew ended up living that hypothesis involuntarily, not by careful research design, but because the farm could not grow enough food. They were still hungry, especially through the first year. The crew reported near constant hunger, and most of them lost a significant amount of body weight. An unusually cloudy stretch of weather cut into the sunlight their crops needed. Pollinating insects included in the sealed ecosystem began dying off, forcing the crew to hand-pollinate many of their own food crops just to get anything to grow at all. Then came the part nobody had fully predicted. The oxygen started disappearing. It began slowly enough that nobody noticed for months. Then it kept falling. From a normal reading of about 21%, the oxygen level inside Biosphere 2 dropped over roughly a year and a half, all the way down to about 14%. Roughly what a person would experience living permanently at an altitude of over 13,000 feet. The crew grew chronically exhausted. Simple chores left them out of breath. Some struggled to sleep properly at night. The cause turned out to be almost absurdly indirect. Microbes living in the facility's rich soil were consuming oxygen and producing carbon dioxide far faster than anyone had accounted for. The plants inside should have been able to absorb that extra carbon dioxide and convert it right back into oxygen. But the concrete used to build the structure itself was quietly absorbing much of that carbon dioxide instead, locking it away in the walls before the plants ever got the chance. Nobody designing Biosphere 2 had modeled that their own building material would compete with their own crops for the exact gas keeping everybody alive. Faced with a crew that could barely function, the outside management team eventually did the one thing the entire experiment was supposed to prove unnecessary. They pumped in oxygen from outside. The seal was broken. not by an accident, but by the plain fact that 8 human lives mattered more than the purity of the experiment. Sit with what that rescue actually depended on. Somewhere just outside the glass, there was a functioning Earth, oxygen tanks, a supply truck, and a team of people willing to break the rules of the experiment the moment lives were genuinely at risk. A generation ship, 400 years from the nearest working oxygen tank, does not get that option. Whatever mistake Biosphere 2's designers made, and quietly corrected from outside, a real ship has to have already anticipated. Its version of this same story does not end with everyone stepping outside 2 years later. Thinner, but alive, there is one more failure worth naming honestly, because a generation ship cannot escape it either. About 6 months into the mission, the 8-person crew split into 2 openly hostile factions, disagreeing sharply over how the mission should be run. They kept working. They finished the full 2 years. They did so as a divided group living inside a sealed glass world with nowhere to go to cool off. Though, notice what actually went wrong here, because it is not what most people expect. It was not the engineering of the walls, the glass, or the airlocks. Every one of Biosphere 2's worst failures came from underestimating biology and human nature. Systems far messier and far less predictable than steel and concrete. Soil microbes nobody had fully modeled. Weather nobody had planned around. Insects that quietly vanished. People who, even after being carefully selected and trained, still split into factions under sustained pressure. Biosphere 2 only had to survive 2 years, with a full team of outside scientists monitoring every reading in real time, ready to intervene the moment something went wrong. Even then, a second attempt the following year, with real upgrades made based on everything the first crew had learned, still ended early, not because the ecosystem failed again, but because of a bitter dispute among the people managing the project from outside. Getting the biology right, it turned out, was only ever half the challenge. Getting the humans right, inside the hull and out, was the other half. Every time, a generation ship gets none of the safety net Biosphere 2 had. Whatever version of this problem shows up on a 400-year voyage has to be solved by the people already on board, using only what they packed, or grew, or built themselves, with nobody outside the hull to call. Every serious generation ship proposal since has treated Biosphere 2 less as a cautionary tale to avoid and more as a syllabus to study line by line. Redundant, overlapping ecosystems instead of one single fragile loop. Continuous, boring, unglamorous monitoring of gases that seem too basic to worry about, until they are not, and harder to design for than any of it. A plan for what happens to the people themselves when the numbers on the food and air gauges start looking wrong at the same time morale does. Biology is only half of what can fail. The facility itself did not disappear once the experiment ended. Ownership passed through several hands over the following decades, eventually landing with a nearby university, which still uses the original glass structure today for climate and ecology research entirely unrelated to sealed human habitation. In a strange way, that afterlife tells its own story. A project built to prove humans could seal themselves away from Earth ended up spending most of its working life studying Earth instead, which is either an irony worth noting or simply what happens to any sufficiently interesting piece of scientific infrastructure once it's original? Headline: Making Purpose has run its course. Every pump, every reactor, every air filter, every single mechanical part holding this civilization together will eventually wear out. That is not pessimism. It is simply what materials do, given enough time. A ship designed to fly for 400 years is not really one machine. It is thousands of machines, each with its own service life. Most of them far shorter than 400 years. All of them eventually needing to be repaired, rebuilt, or replaced by someone on Earth, or even in low orbit. That someone is usually not you. When something breaks on the International Space Station, Mission Control on the ground diagnoses the problem, and a resupply mission eventually delivers the part. That safety net stretches all the way back to entire factories, universities, and supply chains most people never think about. Mines pulling raw ore out of the ground, refineries, machinists, engineers who spent years in school learning exactly this one system. A generation ship has none of it. Once the ship leaves, the entire manufacturing base of human civilization stays behind. Whatever expertise, whatever spare parts, whatever raw materials the ship needs for the rest of its 400-year life, it has to carry, mine, or manufacture on its own. The ship cannot just be a home. It has to also be a complete, self-contained industrial economy, capable of turning raw material into a working reactor part with nothing but what already exists inside the hull. That alone is a staggering requirement. It is not even the hardest part. The harder part is people. The person diagnosing a failing fusion reactor 200 years into the voyage was not born yet when that reactor was built, will never meet the engineers who designed it, and has almost certainly never seen it fail in exactly this particular way before. Manuals help. Manuals are written by people who understood a system deeply enough to predict its failures. Though, once the last person who deeply understood a given system has died, everyone after them is, in a real sense, working from second-hand knowledge, trying to reconstruct expertise nobody currently alive fully possesses anymore. There is a strange, real-world parallel that shows exactly how hard this problem actually is, and it comes from a place you would not expect. Deep underground, in the American desert, dealing with nuclear waste rather than starships. Buried nuclear waste stays dangerous for roughly 10,000 years. In the 1980s, the United States government faced a genuinely odd engineering question, tied to a real facility carved into a salt formation deep under the New Mexico desert, meant to hold radioactive waste essentially forever. How do you warn people 10,000 years from now to stay away from a specific patch of desert when you cannot assume they will speak English or any language currently spoken on Earth at all? A team that included the semiotician Thomas Sebeok was brought in to study the problem seriously. Some of the proposals that came out of that effort still sound almost like folklore today. Fields of towering concrete spikes designed to look threatening in any culture. A strain of cat, genetically engineered to change color near radiation, paired with songs and stories passed down specifically to teach children that a color-changing cat means danger, long after anyone remembers exactly why. Sebeok's own conclusion was more sobering than any single clever design. No single symbol, no single sentence, No single warning sign could be trusted to survive 10,000 years of language change, cultural drift, and simple forgetting, fully intact. He proposed something almost mythological instead. A small, self-renewing group of trained specialists, a kind of standing order tasked specifically with preserving and passing down the warning generation after generation, using ritual and repetition rather than relying on any single physical sign to survive on its own. Decades later, the site is real. It holds real waste. And the warning system built around it is still being debated and refined today, which tells you something on its own about how genuinely unsolved this category of problem remains. Even with an entire government agency and unlimited time to work on it, a generation ship faces a gentler version of the exact same problem, on a much shorter timescale. But the underlying shape is identical. Written manuals alone will not reliably carry deep technical understanding across 250 or 400 years. Something living has to carry it instead. A deliberate, ongoing culture of hands-on training, where each generation does not simply read about the reactor, but actually opens it, maintains it, diagnoses its small problems, and personally teaches the next generation to do the same, long before any real crisis forces the issue. Not a class taken once as a teenager and forgotten, something closer to an apprenticeship that never fully ends, woven into the ordinary rhythm of life on board, the way farming or cooking would be. Skip that step even once, and let one generation grow up treating the ship's systems as simply, permanently working, the way most of us treat electricity or running water. The knowledge gap does not announce itself gently when it finally arrives. It shows up all at once. As a failure, nobody currently on board fully understands. At a moment when there is no factory, no expert, and no way to call home for help, the ship does not just have to carry spare parts. In other words, it has to carry an unbroken chain of people who remember, hands-on, exactly how everything works, and who understand it deeply enough to still say something useful when it inevitably breaks in a way the manual never anticipated. That chain is more fragile and more important than any single physical component on board. Steel and circuitry can be replaced by anyone with the right raw material. Understanding can only be replaced by someone who was actually taught, in time, by someone who still remembered. There is a meaningful difference, worth being precise about, between information and understanding. A ship could carry every technical manual ever written about its own systems, stored 1,000 times over, and still lose the ability to actually operate them. That loss would happen the moment nobody on board can read those manuals with the kind of fluency that only comes from having opened the machine itself, more than once, under real pressure, with real consequences for getting it wrong. Information survives storage. Understanding only survives practice. Keeping a ship's machinery alive across 10 generations is one kind of memory problem. There is a second, quieter kind still ahead of us. One that has nothing to do with reactors or repair manuals at all. Not forgetting how something works, but forgetting why any of it was ever worth doing in the first place. We will need every one of the next several chapters to properly earn our way to that question. Space is not empty in the way most people imagine it. It looks empty. It behaves like a battlefield, right now, as you rest. Two things you never think about are protecting you. A thick blanket of atmosphere pressing down overhead. An invisible magnetic field wrapped around the entire planet, generated deep inside the Earth itself. Together, they filter out the overwhelming majority of the radiation constantly raining down on this planet. From the sun and from far beyond it. Step outside both of those protections, the way any interstellar ship eventually must, and the universe stops being gentle. A physicist who has studied this closely at the University of California in Davis breaks the danger into three separate pieces. The first is the ordinary solar wind, a steady stream of charged particles boiling off the sun. It sounds alarming, but it is genuinely weak, easily stopped by the thin walls of any spacecraft. The second is a solar energetic particle event, essentially a burst released during a solar flare, hundreds of times more powerful than the ordinary solar wind, but still stoppable. With enough water or dense material between the crew and the source. The third is the real problem. Galactic cosmic rays. These are not particles from our sun at all. They are fragments flung outward from exploding stars and other violent events elsewhere in the galaxy, traveling at almost unimaginable energies. In some cases, 1 billion times more powerful than the ordinary solar wind. They can punch straight through hundreds of meters of shielding material without slowing down meaningfully. Worse, when they strike something solid, like the wall of a ship, they can shatter on impact, spraying a shower of secondary radiation, X-rays, neutrons, and other charged fragments, into exactly the space the shielding was supposed to protect. Real numbers describe how bad this gets, thanks to an actual instrument that made the trip. When NASA sent its Curiosity rover to Mars, it carried a radiation detector that recorded the dose the entire way there, during roughly 8 months of travel through interplanetary space, unprotected by any planetary magnetic field. That detector measured a radiation dose rate of about 1.8 millisieverts every day. Add that up across a full round-trip mission to Mars, and an astronaut could absorb a dose close to 1 full sievert, a level of exposure that would not be permitted in any ordinary job here on Earth. For any reason, even astronauts who never leave low orbit are not fully spared. The International Space Station still sits partly inside Earth's protective magnetic field, and its crews still absorb something like 150 millisieverts over a typical year in orbit, compared to roughly 2 or 3 millisieverts a year for an average person standing on the ground. A difference of many dozens of times over. NASA tracks each astronaut's lifetime exposure carefully and limits how many missions any one person can fly because of it. Step past that partial shelter entirely into open interstellar space, and the dose climbs again, this time with no magnetic field left to soften any of it. The damage is not limited to cancer risk, which is usually the only consequence people picture. Laboratory studies exposing animals to the same kind of heavy, high-energy particles found in galactic cosmic rays have documented measurable changes in the brain, particularly in regions tied to memory and learning, along with early cataracts, cardiovascular strain, and slower wound healing. For a ship where reproduction across generations is the entire point of the mission, there is a second, quieter concern layered on top. This same radiation damages DNA directly in the reproductive cells of anyone exposed to it. The shielding question is never just about protecting the people currently alive on board. It is about protecting every generation not yet born as well. Hold that number next to the length of the journey we are actually talking about. A trip to Mars takes, at most, a couple of years. A generation ship is planned for 250 to 400 years. Left unshielded, the accumulated radiation would not just raise cancer risk modestly, it would make the ship and everyone born on it uninhabitable within a single generation, let alone 10 of them. Shielding is not a nice feature to add later. Then, it is one of the load-bearing requirements of the entire ship, as fundamental as the rotating hull itself. Passive shielding, simply putting enough mass between people and the radiation, works reasonably well against solar particles, but struggles against the heaviest galactic cosmic rays, the ones capable of shattering on impact and creating secondary radiation of their own. Some researchers are exploring active shielding instead, generating an artificial magnetic field around the ship, essentially building a small, portable version of the exact protection Earth already gives us for free, deflecting charged particles before they reach the hull. It is an elegant idea on paper, keeping a magnetic field that large running continuously for centuries is its own significant engineering project, layered on top of everything else this ship has to do. Most current serious designs choose to do both at once, and cleverly. Rather than carrying separate shielding as dead weight, they place the ship's water reserves, its waste storage, and its outer layers of soil and growing crops between the crew's living spaces and the open hull, letting mass the ship needed to carry anyway do double duty as a radiation barrier. It is not an elegant solution. It is a practical one, the kind an engineer reaches for when a problem cannot be fully solved, only managed carefully enough to survive. Notice the trade this forces, though, because it never fully disappears. Every extra layer of shielding is also extra mass, and extra mass is exactly what a ship spends 2.5 centuries slowly accelerating and then, just as slowly, decelerating again. Pile on more shielding to protect the crew more thoroughly, and you make the engines work harder for the entire length of the voyage. Trim the shielding to lighten the load, and you trade a small amount of speed for a measurably higher radiation dose. Generation after generation, there is no version of this ship that gets to have both a light, efficient hull and a fully shielded one. Every serious design ends up somewhere in the middle, and reasonable engineers disagree, even today, about exactly where that middle should sit. Every solution to this problem still comes back to protecting soft, fragile human bodies that did not evolve for this environment, and were never meant to. That fragility raises the single strangest, most argued over question in the entire field of generation ship design. Exactly how many of those bodies do you need to bring in the first place? Picture 4. A moment. The smallest room on the entire ship that anyone would ever call sacred. A nursery, a few cribs, a window looking out onto the axial gardens. The low hum of the hull always present in the background, like a heartbeat nobody notices anymore. Somewhere behind the paperwork, the arithmetic, and the arguments in this chapter. This is what the whole question actually comes down to. How many of those cribs need to be filled, generation after generation, for the people who eventually step off this ship to still be in every meaningful sense. Human, you would think, of every question surrounding a generation ship. This would be the easiest one to answer. Ask a geneticist how many people you need to found a healthy population, and get a number. Ask that question honestly, though, and you get several different numbers from serious researchers using serious methods that disagree with each other by a factor of more than 100. Start with the smallest serious estimate. An anthropologist named John Moore worked through the problem using fairly straightforward assumptions. No advanced genetic testing of passengers beforehand. No frozen sperm or egg banks kept in reserve. Just people pairing off and having children the ordinary way, across a journey of around 200 years. Under those conditions, Moore calculated that a starting population of around 160 people would preserve enough genetic diversity for the entire trip, with essentially normal family life the whole way. Tighten the rules slightly, requiring couples to wait until their 30s before having children, and that number could theoretically drop to as few as 80. Now meet the second serious estimate, from an anthropologist named Cameron Smith, published in a peer-reviewed journal called Acta Astronautica, in a paper written specifically to inform the original Project Hyperion research effort. Smith built a detailed computer model accounting for mutation, genetic drift, and the slow accumulation of harmful mutations across many generations, factors Moore's simpler calculation had not fully captured. His conclusion was strikingly different. A genuinely safe founding population needed to be somewhere between 10,000 and 40,000 people, not hundreds. Sit with the size of that gap. One serious researcher says around 150 people. Another, addressing the exact same problem, says you need close to 100 times that many. This is not carelessness. It is two entirely different sets of assumptions about how forgiving human genetics actually is over multiple centuries. And the field still has not fully resolved which assumption is closer to correct. The disagreement comes down to something geneticists call genetic drift, the slow, random loss of genetic variety that happens naturally in any small, isolated population, generation after generation, simply because only some people's genes get passed on and others do not, purely by chance. In a population of billions, drift barely matters. In a population of a few hundred, sealed off from any new arrivals for centuries, it can matter enormously, quietly narrowing the gene pool until harmful mutations that would normally stay rare start showing up again and again. Moore's calculation treated this risk lightly. Smith's treated it as the central danger of the entire mission. Neither is obviously wrong. They built their models around different assumptions about how much that slow narrowing actually costs a population over centuries. And nobody has run the real experiment to find out. A third answer arrived. Stranger than either of the first two, an astrophysicist named Frederick Marin built a detailed computer simulation called Heritage, designed specifically to model a realistic multi-generational crew, mating patterns, accidents, disease, and all. Working with a colleague, Marin ran a version of the simulation aimed at a voyage to Proxima Centauri, a starting population as small as 98 people. He found could remain genetically healthy, not just for a few centuries, for something like 6,000 years, as long as the population practiced what the researchers called adaptive social engineering, deliberately adjusting who had children with whom, generation by generation, rather than leaving pairing entirely to chance. 98. Compare that to Smith's 40,000. These are not small rounding differences. These are entirely different visions of what the earliest days of a generation ship would even look like. A village barely larger than one extended family, or a small city. This uncertainty is not unique to spaceships. Conservation biologists studying endangered animal species on Earth have wrestled with almost the identical question for decades. They eventually settled on a rough rule of thumb known as the 5,500 rule. Roughly 50 individuals to avoid the immediate dangers of inbreeding, and roughly 500 to protect against the slower, quieter danger of losing genetic diversity entirely over time. It is a guideline, not a law of nature. Like every number in this chapter, serious researchers still argue over whether it applies cleanly to a small, deliberately managed human population at all. It is worth asking why a question this important still has no settled answer. After decades of serious study, part of the difficulty is that nobody has ever actually run this experiment on humans, for obvious reasons. So every number in this chapter comes from modeling, extrapolating backward from smaller populations, animal studies, and the mathematics of inheritance, rather than direct observation. Part of it is that the researchers themselves are answering slightly different questions. Moore was asking, what keeps a population from collapsing outright? Smith was asking, what keeps a population thriving, with minimal genetic disease, indefinitely? Marin was asking what the absolute floor looks like if you are willing to manage reproduction actively rather than leave it to chance. 3 related but genuinely different questions, each with its own honest answer, is part of why the numbers spread this far apart. Notice where the real-world design teams actually landed. Caught in the middle of all this disagreement, Project Hyperion's competition rules required teams to design for somewhere between 500 and 1,500 people, comfortably inside Moore's optimistic low end and Smith's cautious high end, but nowhere close to either extreme. That is not a scientific consensus so much as a practical compromise. Small enough to be buildable with technology that exists today. Large enough that most working geneticists would not immediately call it reckless. Getting this number wrong carries real weight in either direction. Aim too small. Trusting Moore's optimistic end of the range. And a single bad decade. An accident. A disease outbreak. A run of infertility could push the population below whatever threshold turns out to actually matter, with no way to bring in new genetic material once the ship has left. Aim too large, chasing Smith's cautious tens of thousands, and the ship itself becomes so enormous that it may never be buildable at all, turning a genetics problem into an engineering problem large enough to defeat the mission before it launches. There is a more intimate way to feel the size of this disagreement, beyond the raw numbers. At the small end of the range, a ship of 98 or 160 people is smaller than most high school graduating classes. Everyone would know everyone. Every face at breakfast would be a face you have known your entire life, related to you by blood or marriage in ways that would take real effort to avoid after only 2 or 3 generations. At the large end, a ship built for Smith's 40,000 would be closer to a small city, full of strangers you might genuinely never meet across an entire lifetime. faces you could walk past in a corridor without knowing their name. These are not just different numbers on a spreadsheet. They describe two entirely different textures of daily life. One intensely, inescapably familiar. The other, something closer to anonymous. And nobody yet knows which texture a human population can actually sustain, psychologically, for 400 years. There is no clean answer to close this chapter with, and that is the honest place to leave it. Somewhere between 98 people and 40,000 people lies the true minimum. And nobody currently alive knows exactly where. What every one of these researchers agrees on, despite disagreeing on almost everything else, is this: whatever the starting number turns out to be, it cannot simply be left alone to sort itself out. Someone, or something, has to actively manage who has children with whom, for generations, on purpose. The very first ethical argument any real generation ship will ever have to settle is not about the ship at all. It is about the most private decision a human being ever makes. And whether that decision still belongs entirely to the person making it, once the survival of an entire species depends on the outcome. Most of the researchers from the last chapter converge on a strategy nobody chooses out of preference, but that nearly everyone reaches once the numbers force their hand: carry a small living crew. Somewhere in the range, Frederick Marin's simulations described, alongside something else entirely, a frozen bank of eggs, sperm, and embryos, potentially numbering in the thousands, carried in cryogenic storage the entire journey, used deliberately over the generations to widen the gene pool far beyond what a few hundred living people could ever provide alone. Picture where that bank would actually have to sit on a real ship, because the picture matters, not beside the nursery, not near the gardens, but somewhere colder and quieter. Rows of small steel canisters kept just above absolute zero by machinery that never sleeps. No windows, no hum of growing things. Just the strange fact that most of the genetic future of an entire civilization is sitting in a room hardly anyone on board ever has reason to visit. Marin's own follow-up research described exactly this combination: a small crew paired with a genetic reservoir, and worked out that a ship built around this model could be as compact as around 320 meters long, small enough to build, genetically deep enough to survive. On paper, this looks like the clean solution the last chapter was searching for. It satisfies the engineers, who need a population small enough to keep the ship buildable. It satisfies the biologists, who need a gene pool wide enough to survive centuries of drift. Freezing embryos is not even speculative technology. It is routine medical practice today, done in fertility clinics all over the world. The open question is whether it still works reliably after not months or years in storage, but centuries. That open question connects directly back to a danger from 2 chapters ago. Frozen tissue is not immune to the same galactic cosmic rays damaging every living crew member's own DNA. A bank of thousands of embryos, stored for 250 years, needs its own dedicated shielding, arguably some of the heaviest and most carefully placed shielding anywhere on the ship, because damage to the genetic reservoir itself threatens every future generation the bank was created to protect. The insurance policy meant to guarantee the mission's genetic survival sits exposed to the one danger capable of quietly ruining it decades before anyone notices. Notice what this solution creates. 2. Because more than one researcher studying this model has flagged the same uncomfortable consequence. A ship built this way effectively has two separate populations of children. Some are born the ordinary way, to parents who are alive, present, and raising them, with names, family lines, and living grandparents somewhere on board. Others are grown from the frozen bank, brought into being deliberately by the ship's own systems whenever the genetic math calls for it, with no living parent at all, raised instead by whatever caretaking system the ship provides. Some analysts warn this risks quietly creating a two-tier society. One group with families and lineage, another treated more like a resource. The ship manufactures on demand. Nobody designing these systems wants that outcome, wanting to avoid it, and actually avoiding it across 10 generations, are two very different things. This is also where the ethical weight of this chapter has to be said plainly. Humanity has already attempted, in its own history, to manage human reproduction deliberately. In the name of improving a population's genetics, it went by the name eugenics, and it produced some of the darkest chapters of the last century. Forced sterilizations, and worse, carried out by governments that convinced themselves the ends justified controlling the most intimate decision a person can make. Any serious modern proposal for a generation ship has to be built with that history sitting directly in view, not as an abstract warning, but as the reason every reputable design insists on incentives, transparency, and consent, rather than compulsion, for exactly the kind of reproductive guidance a small crew's survival may genuinely require. Notice what makes this genuinely different from that history, and what would make it dangerously similar. The old eugenics movements decided, in advance, which kinds of people were worth having more of, and which were not, then used the power of the state to enforce that judgment on living adults. Nothing in the frozen bank model requires anyone to make that same kind of judgment about a living person's worth. The bank simply needs genetic variety, as much of it as possible, which is a fundamentally different goal than selecting for any particular trait. The danger is not that this system starts out that way. It is that a ship under real pressure, centuries in, running low on options, might quietly start treating genetic recommendations as something closer to instructions, one policy decision at a time, without any single moment where the line was consciously crossed. The line separating a healthy version of this system from a dangerous one comes down to a single question. Is a person given information and left free to choose, or given an instruction they are not actually free to refuse? A ship that only ever does the first can call itself ethical with a straight face. A ship that drifts toward the second, even with the kindest possible justification, has recreated exactly the history it was supposed to have learned from. The honest version of this system looks less like a command and more like careful, transparent information, a counsel, or an algorithm, or both, tracking the ship's overall genetic diversity and gently making that information available. This pairing would meaningfully strengthen the next generation's odds. That one would not. The actual choice, who to love, whether to have a child, stays entirely with the individuals making it. In practice, this likely means the frozen bank does most of the heavy lifting the researchers are actually worried about, quietly supplying additional genetic variety into the population every so often, while the living crew is largely left to build families the way people always have, Even a system built this carefully still has to answer an uncomfortable question nobody has fully worked out yet. Who exactly sits on that council? And who watches the council itself, generation after generation, to make sure gentle guidance never quietly calcifies into something closer to a rule? A geneticist trained on Earth will not be alive by the time the ship is 2 generations in. Their replacement will have to be trained on board by people who themselves were trained on board. A chain of expertise about the single most sensitive subject on the entire ship, passed hand to hand indefinitely. Every one of the same fragility problems from 2 chapters back applies here too. Now, attached to something as intimate as who is allowed to know they are a close genetic match for someone they might otherwise have fallen in love with. Whoever, or whatever, holds the authority to make that call. Year after year, decade after decade, is itself the single hardest problem left to solve. Every government humans have ever built was written by people who expected, at some level, to answer for it themselves. Bad laws got challenged by the very people forced to live under them. In the same lifetime, sometimes the same year, a generation ship breaks that arrangement completely. Whatever system of government the founding crew writes on departure day will still, in theory, be governing their great-great-grandchildren 2 centuries later. None of those descendants had any say in writing it. None of them ever met its authors. None of them can vote the founders out, because the founders have been dead for 150 years. This is not a hypothetical problem invented for this episode. 2 of the men who helped design the government of the United States argued about almost this exact question directly, in real letters, in real time. Thomas Jefferson believed no generation had the right to permanently bind the next one. His reasoning was almost startlingly literal. The earth, he wrote, belongs to the living, not to the dead, and no set of laws written by people no longer around to answer for them should be treated as automatically binding on people who never agreed to them. Writing to a colleague in 1789, he calculated, based on the life expectancy tables of his era, that a generation lasted roughly 19 years, and argued that every law and every constitution should formally expire on that same schedule, forcing each new generation to knowingly choose to keep it or rewrite it. James Madison disagreed just as strongly, worried that constantly rewriting the fundamental rules of a society would produce chaos rather than freedom, and that some structures needed to stay fixed precisely so people could actually plan a life around them. Jefferson lost that particular argument, at least on Earth. The Constitution he helped write has no built-in expiration date, and Madison's preference for durable structure, amended carefully rather than rewritten wholesale, is the version that actually governs the United States today. That outcome does not settle which man was right. It only shows that even the people who invented modern Republican government, arguing face to face, with every incentive to get it right, could not fully agree on how much a founding generation should be allowed to lock in place for everyone who comes after. Neither man was designing a spaceship. They were arguing about exactly the tension a generation ship cannot avoid. Too rigid a system, frozen in place by founders gone for centuries. Risks becoming a relic nobody currently alive actually agreed to. Enforced out of habit rather than consent. Too flexible a system. rewritten too easily, risks losing the very stability that keeps several hundred people fed, safe, and functioning inside a sealed hull. There is a second danger layered on top of that first one, arguably the more serious of the two. A ship is not a country with room for slow debate while a crisis unfolds. A hull breach, a failing reactor, a disease outbreak. Any of these might genuinely require someone to make a fast, forceful decision without waiting for a committee. Every serious government humans have built has some version of this emergency power, and history offers a consistent, uncomfortable lesson about what tends to happen to it. Ancien Rome, more than 2,000 years ago, built a formal office for exactly this purpose. A temporary dictator, granted absolute authority for a strictly limited term, meant to handle a crisis and then step down. For a long stretch of the Roman Republic, that system worked as designed. The temptation to simply extend a temporary emergency, rather than formally end it, eventually proved stronger than the rule requiring the office to expire, and played a real role in the Republic's own slow transformation into something else entirely. A generation ship, sealed off from rescue, genuinely facing life or death emergencies on a timescale of centuries, is close to the perfect environment for that exact same temptation to take root, quietly, with the best of intentions, every single time. Some of the most serious modern design proposals try to answer this directly, rather than hoping it resolves itself. The winning entry from the competition described several chapters back proposed splitting authority rather than concentrating it. An ongoing partnership between the living population and artificial intelligence systems, handling the everyday decisions of running a closed civilization. The goal was specific. No single human leader or single dynasty could quietly entrench itself the way the office of Roman dictator eventually did. The appeal is obvious. A well-built system does not get tired, does not build personal loyalty networks, and has no descendants of its own to favor. Notice that this simply relocates the same old question rather than solving it outright. Though, who writes the rules the artificial intelligence itself follows? Who updates those rules 200 years into the voyage? When circumstances the original programmers never imagined start showing up, a system with no ambition of its own is not automatically a neutral one, since it still faithfully carries out whatever values and blind spots were built into it at the very beginning. Unless someone keeps deliberately re-examining and correcting that starting point over time. Removing one point of human failure does not remove the underlying problem. It only changes what the problem is wearing. What every serious proposal agrees on is the shape of the danger itself. A government built for a 4-century mission has to stay legitimate to people who never chose it, stay flexible enough to adapt to circumstances its founders could never have predicted, and stay resistant to the specific, well-documented human tendency to let emergency power quietly become permanent power. Get the ship's engineering wrong, and people die of hunger or radiation. Get this part wrong, and the ship can arrive at its destination fully intact. Reactors humming, crops thriving, governed by something closer to a small empire than anything its founders ever intended to build. A government, even a good one, still has to hold together people who did not choose to be there, confined for their entire lives to the same sealed hallways, with the same faces, for generations. That is a danger with nothing to do with politics, and everything to do with what confinement itself slowly does to a human mind. Humanity has actually run this experiment, deliberately, on purpose, and the results are stranger than most people expect. In June of 2010, 6 men walked into a sealed facility in Moscow and closed the hatch behind them. The experiment was called Mars 500, built and run by Russia's Institute for Biomedical Problems, meant to simulate, as closely as anyone could without actually leaving Earth, what a real round-trip mission to Mars would do to a human crew. 3 Russians, 2 Europeans, and 1 Chinese crew member, sealed inside a habitat with barely 550 cubic meters of interior space, for 520 consecutive days. No fresh air, no sunlight, no view past about 5 meters in most directions. They stayed until November of the following year. What the researchers found was not what a lot of people expected going in. The crew's own self-reports stayed relatively calm and stable for most of the mission. Ask them directly how they were doing, and the answers stayed reassuringly normal. Underneath those self-reports, though, the actual biological data told a quieter, more honest story. Shifting hormone levels, changing sleep patterns, a documented tendency, growing stronger as the mission wore on, to reinterpret unpleasant images and situations in a more positive light than they probably deserved. A kind of unconscious defensive reflex the mind reaches for on its own. There was also a genuinely surprising pattern in exactly when things got hardest. Instinct suggests the middle of a long, sealed mission should be the low point, farthest from both the comfort of departure and the relief of arrival. The data disagreed. The real strain consistently peaked later, in the 3rd quarter of the mission, well past the midpoint. A pattern researchers now call, fittingly, the 3rd quarter phenomenon. It shows up again and again across different isolation studies. Not just this one. The leading explanation is almost entirely psychological. The exact moment the initial adrenaline of the challenge has worn off, and the actual end still feels too far away to draw comfort from. Picture that moment concretely for a second. Somewhere around day 350, deep into a mission with no windows, one of the 6 men would have woken up and realized, with a kind of quiet dread, that the finish line he had been picturing was still further away than the distance he had already traveled. Nothing dramatic happens on a day like that. No alarm sounds. It is simply harder to get out of bed than it was the week before, and harder again the week after that. One more detail. From Mars 500 points directly at where a real generation ship is headed. As the simulated mission progressed, the crew's communication with the outside control center steadily dropped. Fewer questions, fewer requests, fewer check-ins. Researchers read this as a sign of adaptation, the crew quietly building its own internal self-reliance, weaning itself off a connection to the outside world a real interstellar mission would not have anyway. 6 healthy, carefully screened adults, over 520 days, slowly stopped reaching for the outside world and started needing each other instead. Scale the 3rd quarter phenomenon up to a 400-year voyage, and the arithmetic gets uncomfortable fast. If real strain tends to peak somewhere past the midpoint of any sealed mission, a generation ship's hardest psychological stretch. Statistically speaking, would fall on neither end of the journey. Not on the founders who chose this, and not on the arrival generation who finally get to step outside. It would fall on some unlucky generation in the middle, born and raised entirely within the hull, with no memory of departure and no hope of living to see arrival, carrying the heaviest share of a burden neither of the other two would ever fully feel. Mars 500 was a simulation. The real thing has been running for decades already. In Antarctica, every winter, small teams of researchers at stations across the continent are cut off completely for 7 or 8 months at a time, through cold, through total darkness, with no possibility of resupply or evacuation until the season turns. Decades of psychological research on these winter-over crews describe a consistent, well-documented set of symptoms: depression, irritability, sleep disruption, and trouble concentrating. Common enough that researchers simply call it winter-over syndrome. Mood and sleep problems alone account for a majority of every medical diagnosis made on the continent during these months. Interestingly, the cold and physical danger themselves are rarely named as the actual cause. Researchers point instead to something quieter: the sheer monotony of the environment, the total absence of anyone new to meet, and the strain of being stuck, day after day, with the exact same small group of faces. Not every finding from Antarctica is bleak. Long-term studies at Japan's Saiwa station found that many crew members who coped well did so through active, deliberate strategies, reframing hard situations on purpose, leaning on each other for support, planning ahead, and choosing humor over frustration when things got difficult. Isolation does something predictable to a mind. It does not automatically break every mind it touches. What separates the two outcomes looks less like luck and more like practiced, intentional coping, repeated daily, for months at a time. Submarine crews add a third: independent data point to the same pattern, sealed under the ocean for months, with no sunlight and only limited contact with home. Submariners report a strikingly similar arc: a stable beginning, a difficult middle stretch, friction quietly building between crew members confined to the same narrow passageways, a kind of hard-won adaptation as the deployment wears on toward its known, scheduled end. 3 completely different environments, run by different nations, for different reasons. The human mind responds to prolonged sealed isolation in strikingly similar ways every time. Notice the common thread running through all 3 cases. Mars 500 lasted 520 days. A hard Antarctic winter lasts around 8 months. A long submarine deployment might stretch 6. Every one of these missions had a return date. Every person inside knew, with total certainty, roughly how many days were left before the hatch opened again onto a world that had not changed nearly as much as they had. A generation ship offers no such promise to almost anyone born on board. Not 8 months, not 520 days, an entire human life, lived out fully, from birth to death, inside the same sealed hull, among the same limited set of faces, with no hatch that will ever open onto anything different. If 6 carefully selected, psychologically screened adults can still show measurable strain after 520 days with an end date already circled on the calendar. The honest question is not whether isolation will shape a generation ship's population. It clearly will. The honest question is what happens to a person born already knowing there is no calendar circle waiting for them at all. There is a child, somewhere in the middle of this voyage, who has not been born yet. By the time they arrive, everyone reading this sentence will be gone. Their own great-grandparents will be gone too. The ones who actually made the decision to leave Earth in the first place. This child will open their eyes for the first time inside a sealed metal world, spinning slowly through the dark, and they will never, not for a single day of their entire life, have been asked whether any of this was something they wanted. Every other hard question in this episode is at least a problem someone chose to accept on their own behalf. The engine, the food, the radiation, the government, the founding crew signed up. They understood, as much as anyone could, what they were agreeing to. This child does not get that. They inherit the mission the way they inherit the shape of their own hands. Already decided. Already finished. Long before they had any say in the matter. It is tempting to call this simply unfair. And move on. Sit with it a little longer. Though, because the honest philosophy underneath this question is stranger and harder to resolve than it first appears. Consider, for a moment, why this feels different from ordinary bad luck. A child born into poverty, or war, or a difficult family, is also born into circumstances nobody asked them about. And we still call that unfair without much philosophical hesitation. What makes the ship's child feel different is not the hardship itself. It is the fact that every adult who decided this child would exist knew, with total certainty, decades in advance, exactly what kind of life they were choosing for someone who did not yet exist to object. Most parents cannot see that far ahead. A generation ship's founders can. A philosopher named Derek Parfit spent a great deal of his career on a version of exactly this puzzle. His question was almost unbearably simple. If a specific person's entire existence depends on one particular decision, made by people who came before them, can that person really claim they were wronged by the decision? Once you consider the honest alternative for this child is not a version of themselves growing up freely on Earth. Instead, if the crew had chosen differently, decided not to have children on this voyage at all, this exact child, this specific person, would simply never have existed. Someone else might have. Not them. Parfit's point was not that difficult. Circumstances do not matter. They clearly do. His point was that the usual, comfortable way of talking about harm, someone is worse off than they would otherwise have been, quietly breaks down the moment a decision does not just affect a person's life, but decides whether that particular person exists at all. You cannot be worse off than a version of yourself that was never going to exist regardless. There is something almost dizzying about sitting with that for too long. The way staring at a very large number starts to feel less like understanding it and more like falling into it. It does not resolve the discomfort most people feel about this idea. It was never meant to. What it does is quietly remove the easiest, laziest version of the objection. The idea that this child is simply a worse-off copy of some freer child who could have existed instead. There is no freer copy waiting in reserve. There is only this child, in this ship, or no child at all. So the question this chapter cannot fully answer is not whether it is fair to bring a child into a sealed ship without their consent. In the deepest sense, no choice about becoming a parent, anywhere, on a ship or on solid ground, has ever come with the child's consent obtained in advance. Every child born anywhere in human history has inherited a world, a family, and circumstances they did not choose. A generation ship does not invent that condition. It simply removes every soft edge that normally hides it. No sky to walk under. No unrelated stranger to meet by accident. No possibility, ever, of simply leaving to try somewhere else. What a generation ship's designers actually owe that child is not an impossible retroactive consent nobody can ever obtain. It is something more honest and more achievable, a life, once they arrive in it, genuinely worth living on its own terms. Not merely tolerable, not merely survived, purpose that belongs to them. Not just inherited duty, truth, told plainly, about where they are and why, rather than comforting fictions designed to keep them compliant. And the same real freedom every generation before them was owed and rarely fully given, to question the mission itself, out loud, without being punished for asking. Rest here a moment before we continue. This is the quiet, permanent debt sitting at the center of the entire idea, underneath the engines, underneath the gravity, underneath every clever piece of engineering we have walked through so far. Every generation ship ever designed, from a secret envelope in 1918 to a judged competition in 2025, has been, in the end, a very long, very careful argument for why it is acceptable to make this exact choice on behalf of somebody who has not been born yet. Owing that child truth is one thing. Actually managing to tell it to them, 10 generations removed from anyone who lived it, turns out to be its own entirely separate problem. This is a different kind of forgetting than the one we already covered. Losing the technical knowledge to repair a reactor is a mechanical problem, solvable with disciplined training and careful documentation. This chapter is about something slipperier, not forgetting how something works, but forgetting why any of it matters. What Earth actually was, why anyone ever agreed to leave it, and why the metal walls around you are a ship crossing the dark rather than simply the whole of everything that has ever existed. That last possibility sounds absurd until you look at how fast something even smaller than that has already happened. For real, on Earth. More than once. In 1789, a small group of mutineers from a British ship called the Bounty, along with several Tahitian men and women who joined them, settled on a remote, isolated island in the Pacific called Pitcairn. Fewer than 30 people. Total, founding an entirely new, cut-off community. Within a single generation, the children born on that island were not simply speaking English with an accent. They were speaking something genuinely new, a distinct language blending 18th century English dialects with Tahitian grammar and vocabulary, structured differently enough from either parent language that linguists today classify it as its own Creole. By the 1850s, within about 60 years, this new language had fully stabilized into something a visiting English speaker could barely follow unaided. 30 founders, 60 years, one entirely new language, invented essentially from scratch, simply because a small enough group of people were cut off from everyone else long enough. There is something else buried in the historical record of how this happened. Linguists studying Pitcairn's origins have traced an outsized share of its earliest structure back to one influential adult, a St. Kitts-born crew member whose own Creole speech patterns shaped how the very first generation of island-born children learned to talk. One person, in a small enough founding population, quietly became the accidental architect of an entire community's future language. A generation ship's founding population is not immune to that same dynamic. Whoever happens to be present and influential during the earliest years on board may end up shaping the ship's culture far out of proportion to their numbers, entirely by accident, simply by being there first. The story did not stay contained to one island, either. When many of Pitcairn's descendants later relocated to a second island, Norfolk, in the mid-1800s, the two now separated communities developed related but measurably distinct versions of the same original language, still mutually understandable, but drifting apart the moment they stopped sharing a single conversation, split a small, isolated population in two, even briefly, and you do not get one culture in two places. You get the beginning of two cultures. A generation ship starts with a population several times larger than Pitcairn's original settlers, which will slow this kind of drift somewhat. It also runs for 4 to 8 times longer than the span it took Pitcairn's language to fully settle into something new. Language is only the most measurable part of culture. If words themselves can transform this dramatically, so can the deeper things underneath them. Memory, meaning, and the plain, factual story of where everyone actually came from and why. This exact fear has haunted serious thinking about generation ships for almost as long as the idea itself has existed. One of the earliest and most influential science fiction treatments of the concept, written in the 1940s, imagined precisely this outcome taken to its extreme: a ship's population so many generations removed from launch that they no longer understood themselves to be on a ship at all. To them, the vessel simply was the universe, its corridors and decks the entirety of existence. The very idea of stars outside the hull dismissed as religious myth rather than plain fact. It is fiction, not prediction. It has stayed a serious touchstone in this field for more than 80 years. Though, precisely because the underlying mechanism is not fictional at all, it is the same mechanism that built an entire new language on Pitcairn Island in 6 decades. Real modern design competitions take this threat seriously enough to write it directly into their requirements. Teams designing generation ships today are explicitly asked to build in deliberate mechanisms for preserving culture and technology across generations, not simply hoping oral tradition carries the story forward on its own. That likely means redundant physical archives, records etched in more than one material, stored in more than one location. So losing any single copy does not erase the whole record. It means deliberate ritual and education built into the ship's culture on purpose. And, probably most importantly, a founding culture that treats questioning and verifying the official story as a virtue, not a threat. So truth has a fighting chance against the slow, natural pull of myth. None of this fully solves the problem, and nobody claims it does. The alternative, doing nothing and simply hoping accurate memory survives on its own for 250 years, has already been tested. Informally, by history. It took a group of castaways on a single Pacific island, only 2 generations, to invent a new language nobody planned for. A generation ship has centuries, a much larger population to work with, and a genuinely open question about whether the true story of Earth survives the trip any better than plain English survived on Pitcairn. There is a modest comfort worth naming before we leave this chapter. Though, unlike Pitcairn's castaways, a generation ship's founders would know, from the very first day, exactly what they were up against. Nobody explained genetic drift to the mutineers on the Bounty, or warned Ned Young that his own accent would end up shaping an entire island's grammar decades after he was gone. A ship's designers, by contrast, already have Pitcairn's whole story sitting in the historical record before they ever leave Earth. An unusually clear warning: most isolated communities in human history never had the luxury of reading in advance. Every one of these separate dangers — engines, food, radiation, genetics, governance, isolation, consent, memory — finally has to be counted together, honestly, in one place. 16 chapters in, and we have not built a single working generation ship yet. We have built a list. Time to look at that list honestly, all at once, the way an engineer reviewing a real design would, rather than one danger at a time, spread comfortably across an evening. Group the dangers by where they actually come from, and 4 distinct categories emerge. The first is physics itself, indifferent to good intentions. Galactic cosmic rays, capable of punching through, shielding, and damaging both bodies and the genetic material carried for the next generation, at doses that would already be considered unacceptable on a mission, a fraction of this one's length, and a danger we have not named directly until now. The empty space the ship is actually moving through. Interstellar space is not a true vacuum. It carries scattered dust and gas. Even at the gentle cruising speed we settled on several chapters back, a collision with even a tiny grain of that dust releases a genuinely destructive amount of energy on impact. It is the same basic physics that lets a fleck of paint crack a window on a low-orbit space station today. Scaled up by centuries of exposure and no repair yard anywhere nearby, spacecraft engineers already build protection for exactly this problem closer to home. A layered, sacrificial shield, first invented by the astronomer Fred Whipple, designed to shatter incoming debris into a harmless spray before it reaches anything vital. A generation ship needs a version of that idea running continuously, for centuries, without a single gap in coverage. The second category is biology, far less forgiving than steel. A closed ecosystem can quietly poison its own air, the way Biosphere 2's concrete accidentally locked away its crew's oxygen. A population can be started too small and slowly lose the genetic diversity it needs across generations, or started too large and become impossible to build and launch at all. Radiation can damage the very reproductive cells the whole mission depends on, in ways that only become visible generations later, when it is far too late to correct. The third category is engineering entropy, the slow, unglamorous grind of parts wearing out faster than anyone expects, maintained by people who did not build them and may not fully understand them, decades or centuries after the original engineers are gone. Not a dramatic, single point of failure, 1,000 small ones, any single one of which could cascade if nobody catches it in time. The fourth category is the hardest to engineer around, because it lives inside people rather than machines. Isolation reliably strains the human mind, even over months, let alone a lifetime. Emergency power, once granted to keep a crisis from spiraling, has a well-documented historical habit of quietly becoming permanent power instead. And the story of why any of this was worth doing in the first place can drift and blur across generations just as easily as language itself already has. In recorded human history, more than once, none of these four categories actually stays contained inside its own box, which is what makes this list more dangerous than it looks laid out cleanly like this. A radiation event damaging crops is not just a physics problem. It becomes a food shortage, which becomes social strain, which becomes exactly the kind of crisis that tempts a government to grab emergency power it never gives back. A generation that quietly stops believing the official reason for the mission is not just a cultural problem. It is a population that may eventually stop cooperating with the very discipline, rationed resources, managed reproduction, scheduled maintenance, that keeps the other three categories from ever reaching crisis in the first place. On paper, four separate lists. In practice, on a real ship, four ends of the same rope. And a serious pull on any one of them tightens all the others. Picture one plausible version of that chain reaction. Start to finish. A dust grain slips past an aging shield and punctures a section of the agricultural deck. A pure physics failure. Food production drops for a season while repairs are made. A biology failure layered directly on top of the first. The crew assigned to fix it are 3 generations removed from the engineers who originally built that deck, and it takes them twice as long as it should. An engineering entropy failure stacking onto the first 2. Rationing gets imposed to cover the shortfall. Tempers fray faster than usual under a population already carrying generations of accumulated isolation strain, and the council overseeing the repair effort quietly holds on to the extra authority it was granted for the emergency. Long after the deck itself is fixed, one dust grain, 4 different chapters of this episode, each making the next one worse. The first 2 categories, physics and biology, respond fairly well to better engineering and better science. Thicker shielding helps. Careful population modeling helps. These are, fundamentally, math problems. Hard math. But math. And math tends to eventually yield to enough careful work. The third and fourth categories do not yield nearly as cleanly. No amount of clever engineering guarantees that the 40th generation will still remember how to fix what the first generation built, or still believe the reasons the first generation gave for building it. These are not problems you solve once and close out. They are conditions you have to keep actively managing, generation after generation, for as long as the voyage lasts. With no guarantee, any given generation manages them as carefully as the one before. That distinction should shape where a real design team spends its energy first. It is tempting to pour resources into the parts of this problem that feel most like engineering. The shield, the reactor, the hull, because those are the parts a team can actually finish. Sign off, on, and move past. The parts that never finish, the culture, the training, the honesty, are easy to underfund precisely because there is no final version to point to and declare complete. A ship that spends its best engineers on propulsion and its leftover attention on governance is optimizing for the wrong century. There is a reason we know as much as we do about all 4 categories at once. And it is worth naming before we move on. Almost none of this chapter came from theorizing about spaceships in the abstract. Every single danger in this list traces back to something that actually happened somewhere. A real detector on a real rover. A real experiment in a real Arizona desert. Real letters between real founders. A real winter on a real Antarctic station. A generation ship has never been built. And yet, almost every failure mode it would face has already been rehearsed. In miniature. By people who were never trying to build one at all. That is either deeply reassuring or deeply unsettling. Depending on how you look at it. Reassuring. Because it means these are not unknowable risks. Unsettling. Because every one of those smaller rehearsals still came close enough to failure that we remember them by name. A generation ship's most dangerous single point of failure was never really its engine, or its hull, or even its reactor. It is whatever specific chain of decisions. In culture, and honesty gets built into its very first generation. And whether that chain manages to hold. Unbroken. Link by link. Person by person. All the way to the end. If the risks stack this high, is there truly no better way to attempt this at all? There is a better way. On paper. Several of them. Actually, the honest problem is that not one of them is ready yet. And understanding exactly why clarifies something important about why the generation ship, with every flaw we just spent an entire chapter cataloguing, remains the option. Serious researchers keep coming back to, start with the alternative that sounds cleanest. Put the crew to sleep for the whole trip. No centuries of governance to worry about. No multi-generational culture to preserve. No child born who never consented to any of it. Just a crew that closes its eyes at departure and opens them again. Rested. On arrival. We already spent real time with this idea. Back near the beginning of this episode. Real research into human hibernation exists right now. Funded by NASA. Built around a medical technique called therapeutic hypothermia. It is promising work. It is also, as of today, proven only across periods measured in days. Aimed at missions measured in months. For a trip to Mars, nobody currently working on this claims it scales cleanly from months to centuries. And the basic biology of freezing or radically slowing a full, complex, living human body for that long remains unsolved. Not almost solved. Not nearly solved. Unsolved. Wanting this option to exist does not make it exist. The second alternative removes living people from the equation almost entirely. Instead of a crew, send a much smaller, lighter ship carrying thousands of frozen human embryos, along with the robotic and artificial intelligence systems needed to eventually thaw them, grow them in artificial wombs, and raise the very first generation to actually reach the destination without a single living adult on board to guide them. The appeal is real. A ship built this way could be dramatically smaller and lighter than anything carrying a living crew for centuries, since it never needs to feed, house, or govern anyone during the crossing. It also sidesteps the ethical weight of the chapter about the unconsenting child. Nobody is born and forced to live out an entire lifetime in transit, because nobody is born until the ship has already arrived. Look closely at what this option requires, though, and the honest gaps are enormous. Artificial womb technology capable of carrying a human embryo through a full, healthy gestation does not exist yet. Only partial. Promising progress in animal studies so far. Nowhere close to something ready for an irreplaceable human embryo with no fallback if it fails. even if the embryos survive centuries of frozen storage, itself an unproven assumption at that timescale. The first humans to ever exist on this new world would be raised entirely by machines, with no living adult to imitate, comfort, correct, or model what a functioning human relationship even looks like. Every part of this plan has to work correctly. The first time, with nobody available to notice a mistake and fix it. A generation ship can survive a bad decade. A seed ship, by its very design, cannot. Notice, too, that the line between these two options is blurrier than it first appears. Remember the leading proposal from several chapters back: a small living crew paired with a large frozen bank of embryos for genetic depth. That design already borrows heavily from both categories at once. Living generations doing the actual work of raising children and keeping the ship running, while a seed ship-style genetic reserve quietly does the heavy lifting in the background. The real frontier of this research is not a clean choice between two options. It is figuring out exactly how much of each one any single ship actually needs. The third alternative skips people almost entirely and simply sends information instead. We already met this approach, in the shape of fast, unmanned probes, capable of reaching a target star in decades rather than centuries. Whether powered by a laser-pushed sail or a fusion engine burning the same fuel a generation ship might eventually carry, this solves a real and important problem: learning what is actually waiting for us out there before committing anyone to the trip. It does not solve the problem this entire episode has actually been about. A probe can tell us a great deal about a planet. It cannot stand on it. Notice what all three alternatives share. Each trades away something a generation ship insists on keeping. Sleep ships trade away technology that does not exist yet. Seed ships trade away every living adult a child could ever learn from. Probes trade away the humans entirely. A generation ship is not the option researchers keep returning to because it is safe, or elegant, or free of the risks catalogued in the last chapter. It is the option they keep returning to because of the 4 ways anyone has seriously proposed to get a human being to another star. It is currently the only one that does not require inventing an entirely new branch of science first. Every major component it needs: rotating habitats, closed ecosystems, radiation shielding, fusion propulsion, already has a known research pathway today. Real people, real institutions, real published studies, even in the 2 places. Closed ecosystems and fusion power, where the finished, centuries-proven version does not exist yet at all. Biosphere 2, remember, could not even hold its own oxygen steady for 2 years, with a full support team standing by outside. That gap has not closed. It is simply a gap with active, funded people working inside it, rather than an empty page. That distinction matters more than it might first sound. A technology nobody has even started studying might arrive in 10 years. Or in 200. Or never. And nobody can honestly promise which. A technology with a real, funded research program already chipping away at it, however far from finished, can be improved on a known schedule, by known people, using known budgets. Betting an entire species on the first kind of promise is a bet on hope. Betting on the second kind is a bet on effort, sustained long enough, by enough people, across enough generations. It is the difference between waiting for a miracle and simply doing the work that is already visibly, underway, that, in the end, is the entire argument for building one at all. Not that it is safe. Not that every problem in the last 17 chapters has been solved. Only that, imperfect and unfinished, as every piece of it still is. Each piece already has people working on it. Today, using budgets, laboratories, and institutions that already exist. Rather than waiting on a breakthrough nobody can schedule, suppose it works. Though, suppose, centuries from now, against everything just catalogued as capable of going wrong, the ship actually arrives. What does that morning look like? Nobody currently alive will see it. That has been true since chapter 1. And it remains true here, at the very end. Whoever is actually standing in the ship's control spaces on the day the deceleration finally completes was born inside a hull. They will die either inside that same hull or on a world they have never once set foot on. Every day of their life has been spent inside a spinning metal cylinder that was, to them, simply the world. Not a ship, the world, the only one they have ever known, for 400 years. Success meant one thing, and one thing only: keep everyone alive. Keep the reactor running, the crops growing, the air breathable, the peace held, the truth remembered, an entire civilization organized for 16 generations around the single, unglamorous task of not dying before the destination arrived. That is what every chapter of this episode has actually been about. Underneath the engines and the ethics and the radiation. Endurance. Not exploration. Then, one day, endurance is no longer the assignment. The ship has to slow, shedding the same modest fraction of light speed it spent 2.5 centuries slowly building up, easing itself into orbit around a planet none of them chose and none of them have ever seen, with anything other than instruments and old recorded images. Whatever tiny scouting probes went ahead of the ship, decades earlier, will have already reported back on the atmosphere, the gravity, the chemistry, the real, hard data every decision from here forward depends on. Data is not the same thing as a sky. Though, think, for a moment, about what stepping outside would actually mean to someone born on that ship, every person they have ever met, their entire lives, has fit inside a fixed number of rooms and corridors. The horizon, for them, has always been a wall, curving gently upward in the distance, not a line where sky meets ground. Wind is not something they have ever felt on skin. Weather is a word from old lessons about a planet none of them remember, because none of them were ever there to remember it in the first place. Rain, real unscheduled rain, falling without a maintenance crew, choosing exactly when and how much, might genuinely frighten someone raised entirely inside a climate no one on board was ever allowed to leave uncontrolled. Even the sky itself would be strange to them twice over. Strange because it is open, unbounded, nothing curving back to meet itself overhead, the way the walls of home always had. And strange again because somewhere in it, impossibly small and impossibly far, sits the very star their entire family history began beneath. A sun their many times great-grandparents once stood under without a second thought. Now, just another point of light in an unfamiliar sky, indistinguishable to the naked eye from any other. Whatever this crew was, explorers, Colonists. Pioneers. In the vocabulary, the mission started with 4 centuries earlier. None of that vocabulary describes who is actually standing at the airlock now. They are something else entirely. The descendants of people who left, raised from birth to keep a ship alive, now asked, for the first time in 16 generations, to do something none of their ancestors ever had to do even once. Step forward into the unknown, on purpose, rather than simply hold steady against it. Every skill that mattered for 400 years, patience, maintenance, caution, the willingness to keep doing the same careful thing every day without complaint, is not necessarily the skill that matters now. Explorers need a different temperament than survivors do. A comfort with genuine surprise, an appetite for the unplanned. And there is no guarantee that a culture bred for 4 centuries of careful endurance produces people equipped for that shift on command. The moment the airlock finally opens, some of the most serious modern proposals build this transition directly into their planning, treating the final years before arrival as a distinct training period of their own, not unlike the earlier isolation testing back on Earth. This time, preparing a crew not to endure a voyage, but to actually begin one. That is the strange, quiet truth sitting underneath the entire idea of a generation ship. The one thing every chapter of this episode has been circling without saying it plainly until now. This was never really a story about reaching a destination. Destination, in the end, are just coordinates. This was always a story about what a civilization is willing to become. Patiently, deliberately, generation after generation. For the sake of people none of the founders would ever meet. In service of a morning none of the founders would ever see. There is no version of this story where the people who conceived it get to watch it end. That is true of very little else humans have ever built. A building can be finished within a single working life. A war can end within one. Even the longest cathedrals, the ones that took centuries to complete, were still built by people living on the same planet, under the same sky, as the ones who would eventually finish them. A generation ship asks for something stranger than patience. It asks the first generation to find real, complete meaning in a task whose only reward belongs entirely to strangers, born centuries later, who will likely never even know their names. Whether that morning ever actually comes is not a question this episode can answer. Nobody alive today can answer it. It depends on choices that have not been made yet, by people who have not been born yet, using technology that does not fully exist yet. All any of us can do, tonight, is understand exactly what would have to go right, and exactly how much would have to be carried, faithfully, hand to hand, generation to generation, the entire way. And that is where we leave it for tonight. Let the numbers settle. The 250 years, the 400 years, the 98 people, the 40,000 people, the whole long list of things that could go wrong. None of it needs to stay sharp in your mind tonight. You do not have to solve any of it. Nobody has. Yet, right now, on the other side of the world, from wherever you are resting, a small non-profit of architects, engineers, and social scientists ran an actual, real competition to imagine this exact ship. It was judged only last year by people who work at NASA and at universities you could look up by name. Their work helped bring a winning design called Chrysalis into public academic discussion. Nobody involved expects to see it built in their own lifetime. They studied it anyway, argued over it anyway, wrote 100 pages about how its people would govern themselves and grieve and fall in love. Anyway, there is something worth sitting with in that. Every generation ship ever seriously designed, from a secret envelope hidden in a drawer in 1918 to a judged competition decided in our own decade, has been built by people who already understood they were working entirely on behalf of someone else. Not themselves, not their own children, most likely some unnamed, unmet person, centuries removed. Who gets to wake up inside whatever gets designed today? That is not really a story about spaceships. It just happens to be wearing one. If tonight's journey stayed with you, a like or a subscription helps this kind of quiet, careful exploring keep finding its way to more people. There is no pressure in that. None at all. You have already given the last little while of your evening to something patient and far away. And that is enough. The ship has not been built yet. The 250 years have not started counting yet. Somewhere, though, the first sketch of it already exists, drawn by people who will never see it finished. For someone who has not been born, rest now,